El Cimav presenta.
Good morning, everybody. I'd like to introduce to Professor Caroline Ross. She is visiting us from the Massachusetts Institute of Technology. She is Associate Head of the Material Science and Engineering Department. So please welcome Professor Ross.
Well, thank you. Thank you for inviting me. It's a real pleasure to be here in this beautiful place, and I'm happy to do so because Sion and I have been collaborating for a couple of years on a project to do with magnetic thin films. And this is a project that was sponsored by a program called MISTI, which promotes international engagement between MIT and other places. And there's a program between MIT and Mexico which actually allowed us to work together, and for him and his students to visit the US and for me to come here. So I'm very happy to be able to come here and talk to you. So I want to talk about magnetic garnets. So I work in magnetic thin films, and particularly in oxides, magnetic oxides, and garnet is a particular kind of oxide. So I want to show you some of the wonderful properties that this material has, and show you how it can be used in different kind of microelectronic devices. So I think ultimately we might have memories and logic devices like computers and optical communications all using this material. So it's very exciting to me. So let me start by thanking various collaborators. These are students in my group. My colleagues Jeff Beach and JJ Hu at MIT I work with, and then a couple of other collaborators in Prague, in Japan, and in China. So, what are garnets? I think everybody knows garnet jewellery, right? You've seen garnets as a gemstone. So it's usually red, and this is the formula of garnet. So anyone got jewellery, rings or earrings made of garnet? Yes? You know what I'm talking about, right? So this is an actual material, and it's beautiful. Usually it's a red colour, but it comes in other colours as well. So if we take this crystal structure, you can see it has silicon and oxygen. It's a silicate, but it has a lot of other materials in it as well, and it's the different ions here which give you the colour of garnet. So this is the most common formula, and it gives you that red colour. So if we take the silicon and replace it with iron, and if we put iron in this site, and if we put something else in this site like yttrium, we get an artificial garnet, and this is YIG, yttrium 3 iron 5012. So this is the same crystal structure as natural garnet. And there's a picture of the crystal structure. It's actually quite complicated. You can see octahedra. This is an octahedron of oxygen with iron in the middle. This is a tetrahedron of oxygen with iron in the middle. And then these sites here, these dots, represent the site where the yttrium will sit. So we have three different kinds of lattice sites in this garnet. And if we put iron in both sites, the iron is magnetic, and the two orientations of the iron are pointing in opposite directions. So the iron in the octahedral sites points one way, and the iron in the tetrahedral sites points the other way. And because there are two of those and three of those, we have a net magnetization, which is 5 Bohr magnetons per formula unit. And that comes out to 140 EMU per cc, or 140 kAmps per meter, for the magnetization of this material. So that's what we're starting with, this YIG. It's an oxide, it's a good insulator, and it's a ferrimagnet. And its crystal structure is quite large. It has a 1.2 nanometer lattice parameter. So if we replace the yttrium with other materials, particularly rare earths or bismuth or cerium, we can modify the properties of the material. And what I want to do today is show you that YIG itself has very interesting properties. And if we replace the yttrium with other materials, we can get a huge range of properties, electrical, optical and magnetic properties, which allow this material to be useful in a huge range of applications. Okay, so what do we do with garnets? Well, they have a lot of interesting physics and interesting applications. So, for example, these things are commercial magnetic isolators, magneto-optical isolators, and those are diodes for light. They allow light to go one way and not the other way. So this is an essential component of a photonic circuit. Whenever you talk to someone on the phone and that data is going down an optical fiber, there's a diode on the end to make sure the light goes down the fiber but doesn't come back the other way. So these optical isolators are actually essential, and those are made out of magneto-optical garnets. There are a lot of other garnet applications and physics which are maybe not in production but certainly very promising from the point of view of applications. We can make spin wave devices. I'll talk about that a bit more later on. We can make memories. These are holographic memories made of garnet. And we can also study interface and coupling effects between garnets and other materials. This one is a topological insulator, but we can also look at the effect of having heavy metals or other magnetic materials adjacent to the garnet film. So there's really a very rich set of physics and applications that we can do with these materials. So the substituted garnets I'm going to be talking about, we're taking that yttrium and we're replacing it with usually something along here, these lanthanides. And we've looked at cerium, europium, terbium, dysprosium and thulium. Those are the ones we've looked at, or bismuth. There are other things one can put in, but those are the ones I'll be talking about today. And when we do that, thinking of the magnetic properties, the rare earth, which is also a magnetic ion, couples with the octahedral ion, and it's opposite to the tetrahedral ion. So now when we look at the magnetism of these materials, we have to consider the combination of the rare earth magnetism with the iron magnetism, and that can give us some different magnetic properties, particularly changing with temperature compared to what Yig does. In Yig, of course, the yttrium is a non-magnetic ion, so there's nothing here, and we just have the iron. But with any of these others, we get some magnetism that we have to take into account. Okay, so when we're engineering these garnets, I've got here some data that shows you what happens as we go down the series. So this is the series of rare earths, the lanthanides, compared to yttrium in the iron garnet. And we can see the lattice parameter gradually goes down as we go up along the row, because these ions are getting smaller. There's more positive charge at the nucleus, it pulls the electrons in more, so the ionic radius of these ions gets smaller as you go down along the row, and therefore the lattice parameter gets smaller as well. We have changes in the magnetic anisotropy. This is the magnetocrystalline anisotropy, which is always negative, but it varies somewhat in size. However, this is actually quite small. We get changes in magnetostriction, and this is an important parameter for us because this is the parameter that tells us what happens when we strain the material. If we put the material onto a substrate where it's strained, then we will get some magnetic anisotropy, and the anisotropy depends on how big this number lambda is. So some are negative and some are positive, some are large and some are small. So this is a way we can engineer the properties of the garnet by choosing one which has an appropriate magnetostriction. And then finally, the ones in the middle show a compensation temperature. And what that means is that if you look at this magnetic structure, we have iron 3+ in the tetrahedral sites pointing one way and the other two pointing the other way. When the sum of those is equal to that, the material is actually antiferromagnetic, and that happens at a compensation temperature which is different for each of these garnets. So if we plot their magnetization as a function of temperature, some of them go to 0 and then come back again, and that's the compensation temperature. And some of them just change smoothly with temperature. Those ones do not have compensation, and that's an example of YIG, where there's nothing here, so we can't have compensation. So, in summary, by changing the rare earth ion, we can tune a lot of the properties of these materials. And I'll show you later, we can also tune optical properties, which is not on this chart, but we can tune the way they interact with light. Okay, now, we grow thin films in my lab. I know some of you grow thin films by sputtering. We grow thin films by pulsed laser deposition, where we have a laser beam that hits a target. A plume of material is evaporated from the target, and that hits the substrate, which is usually heated up to quite high temperatures. So this is what it looks like. You can see the plume of material coming off the substrate, the target, and the substrate's up there. And by doing it this way, we can get good quality films. This is a TEM image showing lattice match between YIG and a substrate. And we can grow epitaxial films, we can grow polycrystalline films, superlattices, things like that. So this is the way we typically make these films. And one thing I should say is that the common substrate that we use for growing garnets is called GGG, which is gadolinium gallium garnet. This is a paramagnetic substrate, because it has gadolinium in, but you can see the gallium there is non-magnetic. So the substrate doesn't usually interfere with the magnetic measurements. The reason we choose this is because it has a very good lattice match with YIG, so the crystal structure is continuous across the interface. Okay, so now I'll tell you what I'm going to describe about these garnets. I want to start by talking a little bit about magnonics and explain what that is, and show that YIG is actually the best material in the world for this particular application of magnonics. I'll spend some time talking about spintronics, which is spin electronics. It shows how electrical and magnetic properties are coupled in materials, and how we can use that to, for example, change the magnetization using an electric current, which allows us to do electrical reading and writing in a memory or a logic device. And for those, I'm going to talk mostly about rare earth garnets and bismuth garnets. And then finally, I'll show you some photonics. I mentioned before we can make optical diodes out of these kinds of materials. And I want to show you how we can make optical diodes for on-chip photonic circuits, so photonic integrated circuits. Right, so let's start with magnonics then. What's a magnon? A magnon is a collective oscillation of the spin lattice of a magnetic material. So if you imagine each of these red arrows represents the magnetic moment of an atom in a crystalline material, colleagues have worked on, mostly the group in Japan, and this Y-shaped thing is the garnet, the YIG, this black thing, and it's got two inputs and a control input. And then there's an output. And for each of these, there is this thing here is the coplanar waveguide. So what you do is you excite an input here and an input here, and change the phase between them. So obviously, if they're in phase with each other, they'll add up here at the junction and the output will be positive. And if they're out of phase, they'll add up and the output will be nothing. So the output is a logic operation of the inputs, and by having a third line, you can control what kind of logic operation this device does. So, for example, it can act like an AND gate, or it can act like an OR gate, depending on the control, what signal is put into the control. So this is a very simple example of an interference device, but it can form the building block of a magnonic logic gate, because this output can be fed into another one, and you can end up making chains of devices that perform operations using magnons. One thing I should say is that the attractiveness of this is that there's no current flowing in the magnet. The garnet is an insulator, it doesn't conduct any electricity. So these spin wave modes, these magnons, they have very low energy. So the energy is all used in exciting the magnons, and if you can do that efficiently, you have very low energy computing. Okay, so this device is pretty big. The garnet is thick and wide. To scale it down, we can do it all in a thin film geometry. So this one here is made of a 50 nanometer thick film, which is there. And the coplanar waveguides, the input is here and the output is here. Well, actually, these are the two inputs and this is the output. So you can scale down the size of these structures and hopefully eventually be able to integrate them all onto one chip. Now, one thing I should mention about these magnon generation is, so far I showed you that if we have a gold wire, we can use an RF signal, coplanar waveguide geometry, and excite these spin waves. We can also do it another way, and that's by using a platinum wire. And what happens here is that the platinum will excite magnons in the yig by a different phenomenon, a completely different phenomenon that's nothing to do with RF magnetic fields. It's actually due to a spin current which is injected into the garnet. And I'm going to talk about that a little bit later on. But for now, let me just say that this is an alternative way of exciting spin waves in a magnetic material. And what we did here was we used it in an experiment where we could detect this population of magnons that was excited in the yig using nitrogen vacancy centers in diamond. So this red thing is a diamond beam. This was done in Harvard by Amir Jacobi's group. The diamond has a defect in it, which is a nitrogen vacancy defect. There's a nitrogen atom and a vacancy adjacent to each other. And that NV center is actually a very good detector of small magnetic fields. So what they did, you can probe it optically, and you can actually use the response of that NV center to detect magnons in the yig. So this gives another method of detecting magnons and producing magnons compared to those coplanar waveguides. Okay, so let's move on then. We've talked about magnonics. Let's talk about spintronics. So now we have a whole range of phenomena, interesting physical phenomena that we can utilize to make magnetic or spintronic devices. So the most basic one is the spin Hall effect. If you have a current moving in a conductor, the electrons, some are spin up and some are spin down. Well, the spin up ones are deflected one way and the spin down ones are deflected another way. And this is a spin-orbit interaction. It's particularly strong in materials like platinum or tantalum or tungsten, where you have a high spin-orbit interaction. The result of this separation of spins is that now there's a difference in the spin chemical potential, orthogonal to the charge current, and that drives a spin current in this orthogonal direction. So if we have a charge current flowing one way, we'll have a spin current flowing in the orthogonal direction. And we can use that spin current to influence a magnetic material. Now there are some other phenomena we can look at as well. If we have a magnetic material which, for example, has an oscillating magnetic moment, this is equivalent, you can think of this in terms of magnons. The magnons could enter an adjacent layer of platinum or heavy metal, and because that represents a spin current going into the platinum, if we produce a spin current, we're going to also get a voltage induced in the orthogonal direction. That's called the inverse spin Hall effect. And so we can use this electrical effect to measure the precession of the magnetization in the magnetic material. So this is called spin pumping. We can also see phenomena, this is a bit fuzzy, but the spin Seebeck effect is when we have a temperature gradient, it actually drives a flux of magnons in the material, and so we can pump spin current as well by having a temperature gradient. So all of these phenomena can be combined in various ways to enable different kinds of devices. And the thing I'm going to concentrate on most today is that if we have a charge current in a heavy metal like platinum, it drives a spin current, and the spin current will interact with the magnetization of our garnet films and cause them to switch. And that's what's exciting to think of how we can change the magnetization of a material electrically. Okay, so why do we care about using magnetic insulators like garnets? Why don't we just use magnetic metals like cobalt or iron? And the answer is that magnetic insulators don't have any electric current flowing in them. So if I make a structure like this, which has cobalt iron next to platinum, if I pass a current through the platinum, it will also pass through the cobalt iron. And so we'll have all kinds of different things going on, and we'll have a lot more energy being dissipated because it's flowing through 2 layers instead of 1. If I replace this magnetic metal with a magnetic insulator, I know that all the current is going through the platinum, and I can minimize the amount of power dissipation. So the big argument in favor of ferromagnetic insulators, FMIs, is that there's less energy required to do anything, to switch the magnetization, than it would be if you had a magnetic conductor. Okay, so that's the first advantage of it. It also means that we can clearly separate out different effects. For example, if current passes through both layers and the magnetization of this layer gets affected, we don't really know what's going on. We don't know if it's due to the current in the cobalt or the current in the platinum. But for the magnetic insulator, we know that the current in the platinum is the only place where current is flowing. Okay, so what we're going to do then is we're going to make some structures where we have a magnetic insulator, a garnet, and we have platinum on top of it, and we flow current through the platinum. The current flowing through the platinum this way will produce a spin current that way, perpendicular, and that will influence the magnetic film. And so we can get what's called a spin-orbit torque switching. And that can actually change the magnetization of the magnet. On the other hand, if something's going on in the magnetization of the magnetic material, it will inject a spin current into the platinum, and we can detect it through this inverse spin Hall effect. So an injected spin current will cause a voltage in the orthogonal direction. So we have a way of both writing or affecting the magnetization of a material and reading it back using purely electrical means without requiring any magnetic field. Okay, so in order to do that, we need to have these materials having an out-of-plane magnetization. We'd like to have a thin film of garnet with an out-of-plane magnetization in order to observe all of these phenomena. So I'll first of all show you how we can use that in devices, and second I'll show you how we can grow the garnet with a perpendicular magnetization. So first of all, just a little bit of motivation. If you can move domain walls electrically, who cares about that? What can we do with it? So what we can do is make various kinds of logic and memory devices, and I've shown some from the literature. These are some that we worked on. This is from different groups. This is from Carnegie Mellon, this one is from IBM. And in all of these devices, you have a magnetic domain wall which represents a bit of information. And if you can flow a current and move that domain wall, you can write information into the system. So the domain wall represents bits, and we can translate them by a current using this spin-orbit torque effect that I've talked to you already about, or other effects that work in magnetic conductors like spin transfer torque. So that's one kind of device we can make. Another kind goes one step further. If we can make a magnetic wall, then we can make a little magnetic bubble. So these things here, they're called skyrmions. They're special little magnetic bubble domains where the blue represents magnetization pointing up and the red represents down. So in a film with out-of-plane magnetization, you have a little bubble with an in-plane magnetization. That could be a skyrmion. And the difference between skyrmions and simple bubbles is the nature of the domain wall that separates them. So these are very exciting in magnetism nowadays because they can also represent data, but they don't get pinned at the edges of the track because they don't interact with the edge. They just go down the middle. So there's been all kinds of work done on these, and some of you may have heard of this fellow, Albert Fert, yes, maybe? He won the Nobel Prize in Physics in 2007 for spintronics, and he's very excited about these skyrmions, and of course that means everybody else is as well. So, if we want to make skyrmions or domain wall devices, we need magnetic materials with an out-of-plane magnetization or perpendicular anisotropy, so that the magnetization will point up and down instead of side to side in the thin film. Now, how do we get that? Well, we use this effect of strain that I talked to you about earlier. We grow the garnet, in this case it's thulium iron garnet, there it is, thulium garnet, and we grow it epitaxially on that special substrate, the GGG substrate. So you can see some X-ray data here. This is a reciprocal space map. It shows that the material is epitaxial on the substrate, and because of the strain state, the thulium garnet is actually in tension, in plane. And because of its magnetostriction, that gives it an out-of-plane preferred magnetization direction. So we have PMA, perpendicular anisotropy, for thulium garnet on GGG. And here's a TEM picture. The interface is down there, you can't really see it, but the GGG lattice and the thulium garnet lattice, they match up exactly. So these are perfectly epitaxial films, and we can see the gallium and gadoliniums at the bottom and the iron and thulium at the top there. So that's what it looks like in the microscope. In terms of magnetism, these are hysteresis loops measured for out-of-plane fields, and you can see it's a square loop. Low coercivity, we can see domains which are pointing up and down. So black and white means up and down magnetization. So there's no question these films have a perpendicular anisotropy. Now, we can do the same thing for bismuth garnet. This is partly substituted bismuth 0.7, yttrium 2.3. And if we grow that on a slightly different substrate, this is called GSGG instead of GGG, it's still a garnet, but it has a bigger lattice. Then we get this really nice out-of-plane easy axis because of the strain state of the bismuth yig. And if we use another substrate called SGGG, which has a smaller lattice parameter, then it has in-plane magnetization. So you can manipulate the magnetic properties via the strain state. Now, suppose you don't want to use these special substrates for your integrated circuit. You want to use silicon, because everyone uses silicon. So we want to grow films with out-of-plane magnetization on silicon. We can still use strain, but now it's thermal mismatch strain, not lattice mismatch strain. So the strain comes from the cooling down after we grow the film at or anneal it at 800 degrees C, and we cool it down to room temperature. The garnet is in tension, and that gives you an out-of-plane magnetization. And you can't really see it here. This is a TEM picture. The grains are actually pretty big in this film. It's only 40 nanometers thick, but it has grains which are about 10 microns across, and the magnetization is all pointing out of plane on silicon or other kinds of substrates. Okay, so we can make our films with perpendicular magnetization. Now let's do some spintronics on them. So we make a hole cross. This is a garnet cross with a platinum cross. And we're going to flow a current one way and measure a voltage in the other direction. So just a standard hole cross type of geometry. So what do we get for the hole resistance in the platinum? If it was just platinum on silicon, you'd say, we'll get the ordinary Hall effect. And that's the slope here, the ordinary Hall effect. But because the platinum is on top of a magnet, and there's a spin current which flows from the platinum into the garnet, and then interacts with the garnet, and then gets transmitted back into the platinum, we also get a contribution to the Hall effect from that magnetic interaction. And it's called the SMR, the spin Hall magnetoresistance. And we will also see an anomalous Hall effect, because when the garnet changes direction of magnetization, we'll get an abrupt change in the Hall voltage of the of the platinum. And these things have different angular dependencies on the in-plane angle and the out-of-plane angle. So we can separate them out by doing various angular measurements, which I won't bore you with, but just for this case, if you apply an out-of-plane field and switch the magnetization of the garnet, you can see a step in the platinum resistance. So you can see when it switches. Now, what about affecting its magnetization? If we flow a current through the platinum and that spin orbit torque interacts with the garnet, we can actually switch the garnet. So for particular current density, what we're doing is actually translating domain walls in the garnet using the spin current from the platinum. And this can be very successful. We can switch the whole garnet with a 2 nanosecond current pulse. And the currents can be very small. They can be, well, they are small, it doesn't look small, but 10 to the 11 amps per square meter is the current density in the platinum. It's not very many milliamps because the platinum is very thin. So we can have a regime where it switches and a regime switches where it doesn't switch, depending on how much field and how much current we've got. So this is the first time we did this. This was 2017. And then since then it's been improved quite a lot. So this is what the structure looks like now. We have a hole cross still, there and there, in the garnet with the platinum on top. But we also have a gold wire on top, which can be used to produce a domain wall. By flowing a current through here, you make an Ørsted field and it makes a domain wall. And now the current in the platinum can push that domain wall around in a very controllable way. So we can look at different phenomena like how much field does it take to move that domain wall? Well, it moves in fields of a few Ørsteds. It's a very low pinning material. How much combination of field and current does it take to move the domain wall? Well, we can measure that as well. In this case, 35 Ørsteds was applied in plane, and the garnet switched at a current density of about 0.7 times 10 to the 11 amps per square meter. So you can probe all the conditions that lead to switching. And the big question is, how fast will it go? So it turns out the answer is extremely fast. And this here is the speed of the domain wall in a bismuth-Yig film. It's nearly 4.5 kilometers per second, which is pretty amazing. So this is actually the fastest domain wall velocity reported. They usually go at a few hundred meters per second in metals. And so the question is really, why is this so good? What's so special about this material, this bismuth-Yig? And also the thulium garnet I've been talking about. These are some different samples of thulium garnet, and their domain walls go at a measly 2 kilometers per second. Still pretty good. We were excited about this until we saw that. The magic thing about the thulium garnet one is that this domain wall velocity, you can get it even when there's no applied field. There is zero field applied in this experiment. It's just the spin current from the platinum that's moving the domain wall in the thulium garnet. However, in the bismuth garnet, if you try that, nothing happens, and that's why we never bothered with it much. But it turns out that if you apply an in-plane field, then it does move, and it moves extremely fast. So what's going on is the next question. Why does it do this? And so this is a little involved, but I'll try and explain it in a straightforward manner. It all depends on what kind of domain walls are present. So in the case of, if you look at a domain wall in a film with a perpendicular anisotropy, the domain wall can be a nail-type domain wall where the magnetization is going from down to up via this direction, which is perpendicular to the plane of the domain wall, or it can go via a block wall where the magnetization rotates so that it's parallel to the domain wall at the center of the domain wall. And by the geometry of these devices, this doesn't actually give you any domain wall velocity if you apply a current in the platinum. These are the only ones that work. So you have to have this kind of domain wall. So what this tells us is that the thulium garnet has this kind of domain wall, but the bismuth garnet has this kind of domain wall. So why should that be? Well, this is the expected kind of domain wall, and this one is not. And the reason this one is present is because of an interaction called the Dialoshinsky-Maria interaction, or DMI, which is a kind of exchange interaction that favours non-collinear magnetism. So normally we think of exchange as making things parallel or anti-parallel if it's negative, but the DMI makes them have a particular angle with respect to their neighbours. And so it favours a kind of chirality in the domain wall. They're either all left-handed or all right-handed, but you don't get a mixture of them. And this all left-handed domain wall is what's happening in the thulium garnet. So thulium garnet has DMI, but bismuth garnet does not. And that's why we got this result, where these will translate in zero field because the DMI is making their domain wall snail type. This requires an in-plane field because the DMI has to create a nail wall out of something which is not a nail wall. So that's the short answer to that. So I don't want to go into this much more, but just to say that we can measure these DMI effects, and it looks like, curiously enough, the DMI is coming from the interface between the garnet film, thulium garnet or terbium garnet, and the GGG. It's not coming from the platinum interface. So by engineering the bottom interface, we can play around with the DMI. And it must be something to do with the rare earth because it doesn't happen in bismuth garnet. So beyond that, we're still working on it. One other thing is that DMI is essential to make skyrmions. So because we have a DMI which is fairly weak, it's still big enough to create skyrmions. And these are pictures of those little bubbles, those skyrmion bubbles, this is in thulium garnet, measured with Stixum, which is a scanning transmission X-ray microscope. And these things are actually skyrmions. So now we can maybe think about making those skyrmion memory devices. Okay, so there's a lot of rich opportunities here for interesting physics and devices with these magnetic insulators. All right, now the thing I'm going to finish off with is optics. So it turns out that these garnets are very good optical materials in the near infrared. And the reason we care about that is because when you do optical communications, you have a laser, you have a modulator which chops the laser light, and then you send it down a waveguide like an optical fiber, and then you detect it at the other end. And somewhere along the line you need a diode to make sure that the light leaves the laser but doesn't go back into the laser, because that destabilizes the laser. So people want to make all of this stuff on one chip, rather than having discrete devices, so that you can have a photonic integrated circuit. So the photonic integrated circuit would include lasers, which can be made on chips, modulators, waveguides, detectors, but you still need this diode, this isolator. And so that's where the magneto-optical material comes in. And this is the missing component in photonic devices, photonic integrated circuit. So how does it work? Well, I showed you these earlier. These are commercial diodes for light. And it contains a chunk of a magneto-optical material, which is magnetized parallel to the direction of propagation of light. The light is plane polarized. It goes through and it gets rotated. This is the Faraday effect. So everyone probably knows the magneto-optical Faraday effect. So the direction of rotation depends on the direction of magnetization. So if I send light through, it gets rotated by 45 degrees. If the light comes back again, it goes through another 45 degrees in the same direction, and now it's in this direction, so it gets blocked by the initial polarizer. So that's how an optical diode works. What's inside these things is two polarizers, one crystal of garnet, and a magnet. That's all there is inside them. So we want to be able to make materials to do this on chip. We need the material to have a good figure of merit, so a high Faraday rotation, a low optical absorption at the relevant wavelength, and we need to be able to grow it on a silicon platform. Okay, so it turns out that for years and years, this is back in the 70s, it's well known that bismuth garnet, bismuth yig, is a good material for Faraday rotation. It's been very well studied, and this is the effect of the photon energy. The ones we're interested actually are off the bottom here at 0.8 eV, is where we care about. Cerium yig is also a good material, and it has quite a high Faraday rotation. This is thousands of degrees per centimetre. So if you go back to this, you only need 45-degree rotation, so you only need a tiny fraction of a centimetre length in order to get this to work with cerium yig. So those are the materials we're going to work on, and so we characterised the behaviour of cerium yig. This is the near infrared, this end of the plot. And you can see the figure of merit, degrees per decibel. So how many degrees of rotation per decibel of loss? It can be hundreds. So we have very low absorption in these materials. So this is a good thing to start with. And now we have to grow it onto a device, grow it onto chips. So there's a silicon substrate. It turns out that for cerium yig, if we grow it directly on silicon, it doesn't crystallize properly. But if we put a layer of yig on top, it does. So cerium yig is not very stable. It produces cerium oxide and yttrium oxide and iron oxide. But if you grow it next door to yig, then it crystallizes as garnet. So we can use this process to make thin films of cerium yig. We can also make bismuth yig on silicon the same way. And these things have very good figures of merit. So it can be hundreds of degrees per decibel, so very good material for these optical isolators. This is actually the best one reported for a thin film, polycrystalline thin film. So now we've got to make a device. So how is the device going to work? It turns out that the method I showed you before, let me just step back to that. This kind of thing with two polarizers and a piece of garnet in between that's magnetized that way, this does not work on a chip. And the reason is birefringence. If the light is going through a waveguide, we have a birefringence which makes this an ineffective way of doing optical isolation. So we're going to do something different. And that is, we're going to use a device like a resonator, where we have the light going down the waveguide here, and we have a resonator, which is a circular piece of waveguide, next to it. If the light couples into the ring, it just goes round the ring and it gets dissipated. If the light does not couple, then it goes straight through. So what we do then is make sure that the forward propagating light is not resonant, but the backward propagating light is resonant, so it gets picked up and it goes round and round until it's lost. And that's how the isolator works. So to do this, we put the magneto-optical material into the resonator, but we magnetize it sideways instead of lengthways. And that gives you what's called a non-reciprocal phase shift. So if you like, it changes the refractive index for light going one way versus light going the other way. Now we can do this in two geometries, the ring resonator I just described, or an interferometer geometry, which is actually better, where the light is split into two arms, and one of them has a positive phase shift and the other has a negative phase shift, and it depends which way the light is going, whether those two phase shifts will add up or subtract. So that gives you a better type of device. So now we can put all of this together and make some real devices. One thing we have to do is think about the mode of the light. The light can propagate in these rectangular waveguides either as transverse electric or transverse magnetic modes. And it turns out that in order to get these devices to work, we have to decide which mode we're going to use. And we have to arrange the garnet, this material here, in the appropriate geometry to get the correct isolation of either TE or TM mode. So I'm not going to go through all of this, but you can do some modeling. And for the TM mode, we need to put the garnet on top, but not underneath. At least we have to break top-bottom symmetry. For the TE mode isolation, we have to break left-right symmetry. And so we have to fabricate the devices a little bit differently. And we can go ahead and do that. This is the first one we made, garnet on top of silicon waveguide. These are TM devices, and they do actually work. They're not great, but they work reasonably well. They do have a lot of loss though. And so we continue to improve that. And this is now the best one. So this has an isolation ratio of 40 dB. That's the difference between forward and backward light propagation is 40 dB. And it only loses 3 dB of the forward light. So it loses 43 dB of the backward light and 3 dB of the forward light. And there it is, it's a ring resonator, and the garnet is actually underneath instead of on top. This is a Max Ender device which also works, in fact, much better. It gives us 30 dB isolation and 6 dB loss. And then we can go through and do these TE mode devices by growing the garnet on the side wall of the waveguide. So there's the waveguide, garnet grows on the side there. And if we can do that, then we can get TE mode isolators. They're not quite as good because the garnet growth isn't quite as good. But these are the first integrated TE mode isolators. And the reason that's important is because on-chip lasers actually make TE mode light. And there's a TE mode isolator made in a Max Ender. So the upshot of all of this is that these garnets are really good materials for making on-chip optical devices. And because they can also do spintronic and magnetic phenomena, then we could imagine a path to making electrical and optical and magnetic phenomena all coupled together in one device. You could have an input which is optical, you could have an output which is magnetic or spintronic. There's all kinds of things you can imagine doing. So that's the story I want to leave you with as we finish the talk. So I hope I've shown you that these materials are a wonderful playground for doing interesting physics as well as interesting applications. They're insulating ferrimagnets. We can tune their properties via their composition. The prototypical one, YIG, is the best thing for magnonics because it has the lowest attenuation of spin waves. These other substituted garnets can have perpendicular anisotropy, and that makes them really good for spintronics, like domain wall motion, in fact the fastest domain wall motion ever recorded, as well as things like skyrmions and chiral textures. And then they also have these optical properties, particularly bismuth and cerium garnets, which allow us to use them as integrated on-chip optical devices. So I think these materials have great potential in all kinds of spintronic, magnetic and optical devices. So thank you very much.
Cápsulas de ciencia.
Centro de Investigación en Materiales Avanzados. Cimav.